apparently the little wheel is spinning and we are recording. Okay, so where we ended our time together on Wednesday of last week was we had begun a discussion of the science of the study of matter. And the science of the study of matter is chemistry. And that's pretty much our topic of this semester. I'm going to continue today with a little more just brief introduction to where we are today and how we got to where we are today as chemistry and the study of matter matured over the time of humans on this planet. Now, again, just as a brief recap of where we were and where we have reached. Chemistry was not formalized for a long period of human existence. Humans had more things to concern themselves with than to worry about how matter behaved and the interactions of the materials that make up our everyday lives. We were just worried about surviving rather than concerning ourselves with these interesting but seemingly at the time not necessary questions as to how everything works. And so slowly over time, as humans began to have at least a little bit of time to breathe and a little bit of time to think about their surroundings and their interactions with their surroundings as to exactly how and what is matter and how the interactions of matter can be predicted, then the science of chemistry began to formalize. Now, again, I want to point out, though, that certainly for several millennia of time, chemistry was thought to be hocus pocus, magic almost. And the people who practiced chemistry used it more as a means to gain advantage than as a means to understand the workings of the world. What I'm getting at is that we used it in order to frighten people, or to gain power over people, or to entertain people, or to dupe people, take their money. As I mentioned a few examples of how that was carried out by wizardry and things of this sort, or transmutation of lead into gold and various other schemes and entertainment things that were pulled off by people who were practicing chemistry. And one of the hallmarks of this was you had no desire to share with others your tricks. Because if everybody realized that these weren't supernatural occurrences, then there was less entertainment value or less fear value that they could gain from this public display of these sorts of things. All right, so finally, around the 1700s, it began to mature as a science. And it matured as a science, particularly with a few individuals I mentioned at the end of our time together. And that was Aljabeer, who wrote a premise or a textbook, if you like, showing how certain physical processes worked, and literally some procedures and explanations of how you can carry out systematic studies of certain forms of matter. And in the Western world, Antoine Lavoisier, who actually got a copy of his book, and his wife and him translated it and also added to it a little bit and did a little bit of stuff with it, but then published a Western version of the study of matter, and it became sort of the starting point, if you like, for the academic treatment of chemistry as a study of the properties of matter. Okay, so that's where we are now, and we're going to continue in this theme of moving towards our understanding of the behavior of matter. And what I'm going to do is hit the present now button. And as I have in the past, of course, I'm going to go to my slides, and I'm fogging up a little bit here, and I want to share, I guess, don't I? I guess I want to share that, I guess. So I am sharing, and now when I hit this, and I'm sorry, I'm leaning in so close to everybody because I'm pretty annoying, I know. I want to go from the slideshow from the current slide. Okay, so this is the individual. This is where we are now. We're moving, we're approaching the time of the establishment of the United States, but still most of the action in the Western world was occurring in Europe. And I turn from Lavoisier to this individual named John Dalton. And as I like to do, I would like to humanize him to a certain extent, to say a few words about his contributions and some of the things that he's noted for with regard to his place in the history of science. John Dalton was a very celebrated educator and public communicator. And that's probably why this idea of the atomic theory of matter is in all textbooks and in all sources of reference. This is the fellow who is really described as the person who concretely established the basic rules of understanding matter. So he's the guy that everybody turns to in terms of what is known as Dalton's atomic theory, so that we can describe how the world around us works. Now, as I mentioned a moment ago, the key of John Dalton's success was his ability as a communicator. He was a great public speaker. He was a great educator. He was famous for establishing several schools in his days in the mid 1700s and the late 1700s and early 1800s. He was instrumental in academics and the advancement of academics at the upper level, if you like. We got to remember at this time, universities were being established. Universities had been around for 100 years, and he was one of the people that helped the flourish of the university academic structure in Europe. And one of the things that people at this time did, now you got to remember, is particularly in the urban settings, they had opera and they had plays, but they didn't have professional sports and all these other distractions that we now have that can take up our time. One of the things that was very commonly done in the early 1800s and late 1700s were that scientists would give public displays. A scientist would give a lecture in a huge auditorium, kind of like a concert, and the scientist would present current ideas and explain things and try to give demonstrations of things that were occurring in the developing, maturing of science. And John Dalton was very famous for this. He would hire out an arena or an auditorium and bring some chemicals and things with him and give a public demonstration. And they were quite well received. They were entertaining and they were informative. And in this regard, the stature of John Dalton grew and grew and grew. And I would offer to you that this is why he is given credit for being the person to come up with this atomic theory. What I'm getting at with that is that he didn't really make this up. Many of his contemporaries believed the same things as him at this time, but he was very good at espousing it, at spreading the gospel. So in the primers that you read now, he's given the credit for doing these sorts of things. Now, other things of interest about John Dalton was he had a real strong interest in weather. He loved to concern himself with the climatic conditions and understanding them. And for about 40 years, he kept extremely detailed records of the temperature, barometric pressure, wind directions, precipitation rates and levels throughout England. And he kept very detailed records of this stuff for decades, on daily detailed records that later climatologists borrowed from. They took his detailed studies and it helped them develop the models that they use now for weather patterns. Okay, it's getting pretty remarkable. When I was a kid, the prediction of the weather was really a prediction. Nowadays, you get on there and you put the TV on, they say, Well, in 3 days, we got this thing coming this way, and it's going to be here in 3 days, and we're going to get a couple of days of serious rain. And they might be off, 12 hours or so, but they pretty much are getting it. They're figuring these things out. Well, these computer models, which are now able to predict the weather, have to base their understanding of what the weather is going to be on their own model, and that model required massive amounts of data. And this massive amount of data was begun by this individual and his mundane routine of writing this stuff down. To you or I, that might be like, I'm not writing down. That's just crazy. I don't want to spend an hour of my day going around and categorizing the climatic conditions and the precipitation rates and the barometric pressures and all these sorts of things. That just doesn't interest me. Well, it's important that people like him took the time and effort to do such things because it enabled us to further the whole idea of climate science, even though he's not even at all noted for climatology at all, but I'm telling you, his contributions in that regard were very important. Okay, so enough to say about John Dalton. Let's look at his ideas in what's known as Dalton's atomic theory. It's 4 basic premises that now we are going to use to govern our understanding of the behavior of matter. The first of them is that all matter is composed of small, indivisible particles, and he even called them atoms. And the word atom, if you remember, I mentioned to you, was used 2,000 years before this by a fellow by the name of Democritus, and he was the mentor of another individual named Leucippus. They spread this word in the times of ancient Greece well before the birth of Jesus. They were using this idea of indivisible building blocks, and indivisible in Greek means atomon or some word of that type. And so he went back to the word that they had used for these indivisible building blocks that all matter is made from. If you recall, what I said had happened was after Democritus espoused this idea, along came Aristotle and said everything was made of earth, air, fire, and water. And pretty much Aristotle's prowess as an individual and importance as a person kind of dominated, and that was kind of the way things were thought for a long, long period of time. So finally, here in the early 1800s, we have returned to the indivisible building block idea. We have returned to atoms. Then second, if you have an element, now, and let's remember this, I mentioned element when I had talked about Aristotle. Aristotle had his earth, air, fire, and wind, or earth, air, fire, and water, were his 4 elements, and that's a Greek word, element. And that word element is, again, another word that Dalton is going to use and his contemporaries. I'm going to remind you that I don't think Dalton really, truly, solely came up with these ideas, but they were shared among his peers at the time, and he spread the word about them very effectively. But in any event, he came back to the concept of the element, but instead of Aristotle's concept of the element, he chose to say that this would be a large collection of atoms. Every one of these atoms in the same element was identical. So if you have a pure element in your hand, and it's enough of that element that you can see, actually at the nanoscopic level, there are gazillions and gazillions of them in your hand, and each of them is exactly the same. So that's this idea of an element. An element is a huge collection of the same exact type of atom, and you have to have a huge collection of them because individually they're so tiny. And so then you can have the properties of an element based on the collective behavior of a huge number of exactly the same particles. Okay, then the third idea, which is where we're really hitting the road of chemistry. Now we're really getting to how chemistry works. When atoms combine in definite proportions, they are forming the same compound. Anytime they combine in a definite proportion, you're making the same stuff. If they combine in multiple proportions, you're making different stuff. Okay, now what does he mean here? Very simply, if I take 12 grams of carbon, I weigh out a pile of 12 grams of carbon. I weigh out a pile of 16 grams of oxygen. And I take the 12 grams of carbon, react them with the 16 grams of oxygen, I will make 28 grams of stuff because matter is conserved. I'm not going to create or destroy the matter. So if I take 12 of this and 16 of that, put them together, I'm definitely going to get 28 grams total. Well, not only am I going to get 28 grams total, I'm going to get a specific ratio and proportion of combination between the carbons and the oxygens. The stuff I make is different than the individual carbons. The stuff I make is different than the individual oxygens. It's a new material formed by this combination. And as a matter of fact, what it is something your mom and them have heard of. It's carbon monoxide. So 12 grams of carbon combining with 16 grams of oxygen exactly, well, not, be careful with our measurement of the numbers, but if I combine them all together, we will say I'm going to make 28 grams of carbon monoxide. The point of the definite proportions would be, now let's take 24 grams of carbon. And if I want to form carbon monoxide from the 24 grams of carbon, since I'm now using double the carbon, I had better do the same definite proportion of the oxygen. So if I use 16 grams of oxygen originally, and I doubled my carbon, I had now better use 32 grams of oxygen. So 24 grams of carbon plus 32 grams of oxygen will make now 24 plus 32, which is 56 grams of carbon monoxide. And likewise, if I take 120 grams of carbon, I will need 160 grams of oxygen combined together, and then I will make carbon monoxide, and now I will be making 280 grams of it. And I combine the masses of the individual things. That is combining in definite proportions. Okay, but what I would say in regard to the multiple proportions, what if I took 12 grams of carbon and instead of combining them with 16 grams of oxygen, I combined those 12 grams of carbon with 32 grams of oxygen? I'm still going to form a new material. It's not the same as the original carbon. It's not the same as the original oxygen. And it's not the same as the carbon monoxide because I am now forming a multiple proportion. To make carbon monoxide, I took 12 grams of carbon combined with 16 grams of oxygen. Now I'm combining 12 grams of carbon completely with 32 grams of oxygen. And now what I'm making, I think maybe many of us in here could anticipate, I'm making carbon dioxide. It has twice as many oxygens per carbon as carbon monoxide. So the point would be, when I have a 1-to-1 ratio of the carbons to the oxygen, I'm going to make carbon monoxide. When I have a 1-to-2 ratio of carbon to oxygen, I'm going to make carbon dioxide. If I had a 1-to-3 ratio, I'd be forming another new material that would be carbon trioxide, if you like, and I could even have carbon tetroxide if I combined one carbon to every 4 oxygens. So that's the idea of combining in definite and multiple proportions. This, again, as I would point out to you, is really where the chemistry is beginning. When we're starting to look at the ratio and proportion of starting building blocks and forming new materials from the building blocks. Okay, then finally, the last of Dalton's ideas is that if we have a so-called chemical reaction, which is a change of composition of the material into new materials. That's essentially what chemical reaction means. I start with A and B, and after they fool around with one another, maybe energetically or for various other reasons, they want to get together. I might have to input energy. I might get energy released. And these are things that will come about in later discussions. But when I start with A and B and later time open the pot, A and B are gone. Now in the pot are C and D, materials with completely different properties. Maybe some similar properties, but certainly they are characteristically different than the A and B starting materials. So that is what I'm calling a chemical reaction. The chemical reaction is often not just manifested by a change from one material into another. It's manifested with other kinds of changes. Like what? Like change in phase, like change in material properties, like hardness, pliability, ductility or bendability, all these other things that might go with it. And very commonly, change in energetics. As a matter of fact, this is one of the main reasons we do chemistry. We really do the chemistry not to harvest new products from the chemistry. We do the chemistry to harvest energy. You did that today when you poured gasoline into your engine and got here. You're doing that right now if you're standing here waving your arms around. You're doing chemistry in your body to harness energy from reactions between oxygen in the air and food that you've ingested to generate energy that is converted into electricity that enables my tendons and things to push and pull on my arms and mechanically move me around. So all these sorts of things are done not really to make new materials, but to harness and generate energy from the transformation of these materials. That is more often than not why we do chemistry. We do chemistry for the energetics that results from the chemistry, not so much to make things. As a matter of fact, you can take it to the bank, over half, way over half, I would say, of the chemistry that occurs is not in the, for the purpose of making some new material. It's literally for the purpose of harnessing energy and harvesting energy. Okay, so in a chemical reaction then, where this transformation undergoes, the important thing about the transformation is that the original starting material is gone. What does that mean? It's ripped apart. And there are new materials being formed. That means things are gathering together to make these new materials. Well, the point of statement 4, the very important point of statement 4, is that there are certain building blocks in the things that have been ripped apart. Those building blocks are conserved in the chemical reaction. Meaning, if you have a bunch of hydrogens, oxygens, and carbons in the original reactants or starting materials, you now rip them apart to reassemble into product molecules. Every last hydrogen atom from the things you ripped apart is accounted for in the products. Every last oxygen atom that came ripped apart in the reactants is somewhere in the products. Every last carbon atom that was ripped apart in the reactants is in the products. So that's conservation of matter. Every atom is conserved. So the atoms are rearranged in the chemical reaction. They are not created. They are not destroyed. Now, the importance of the rearrangement, though, is there's different energetic relationships between the way they exist when they were the starting materials compared to the way they exist when they're the finishing materials. Let's suppose it takes less energy to build the finishing materials than it took to build the starting materials. That's kind of important to us because there's energy stored, we say, in the starting materials. As they rip apart and recombine to make the finishing materials, now not only are the particles conserved, the energy is conserved. So if there's excess energy left over from taking apart the things you started with, then building the things you finish with, that is energy we harvest. It comes off of these beginning materials in the form of heat, in the form of light, in the form of pushing the air apart, because it pushes the atmosphere out of its way, in the form of sound that is made as the fire burns or something of that sort. So in some way, the energy stored up in the connections between the original building blocks is now released and transformed into new forms as the products don't need all that energy that was begun with. This last idea, again, is one of the premises and very important foundations as to why humans began to do chemistry in the first place. We wanted to rearrange the atoms and then harvest the energy difference between what you needed to start and what you got out at the end. Now, please keep in mind, not all reactions will release energy. They only release energy when the finishing materials require less energy to build than the starting materials. Typically, if you're making less complex materials, it took more energy to build the more complex materials, so there's extra energy left over. So when we burn a fire, we're taking this very complex formation of connections of atoms, like a tree, and we're taking it apart to make little carbon dioxide things that are floating up in the air, a little bit of water vapor floating up in the air, some carbon monoxide floating up in the air, and a whole bunch of little carbon particles. That's the smoke and the soot that flies off the fire. Much less complex things result, and there's plenty of excess energy that is left over from the massive amount of energy it took to build the tree compared to how much energy it took to build the carbon soot, the carbon dioxide and carbon monoxide molecules, and the water vapor that's evolving off the fire. So there's a lot of heat, there's a lot of light, there's a lot of pushing the atmosphere out of the way by these things as they come off. There's a lot of sound that comes as the fire burns. Now, another interesting thing to keep in mind, though, as I said to you folks, energy is conserved. So if all this energy is released when we burn the fire, that means the starting materials had a lot of energy stored in them. Where in the heck, how did all that energy get stored in them? Well, let's think about where that tree came from. That tree grew out of the ground, and what supported the growth of that tree is one important factor supported the growth of that tree: the sun. The sun bathed that tree for years in energy, and the leaves on that tree were designed to harvest the energy from the sun, take the carbon dioxide out of the air, take water sucking up through the ground, put these things together to build the complex molecules that took so much more energy to make the tree alive. So there's a big cycle of energy here. The tree stole the energy, not stole, borrowed that's a better way to say it. It borrowed the energy from the sun, stored the energy in its connections of the atoms that built the tree, and now humans are releasing that energy and passing it on to themselves in the form of heat or light as they burn, or they do a chemical reaction taking apart the tree. The chemical reaction is what we call burning it, but that's showing you just how much of this energy there is available from the take apart of the tree. Tons of energy evolving from that dismantling of those intricate connections that it took a long time to put together. Okay, now what I want to point out to you is that this was an incredible advance in the systematic maturity of now understanding the relationship of matter and how matter can energetically and connectively, or whatever I want to say, I don't have a really good word to put here, how the building blocks, the basic building blocks of matter can now be used by humans or put together by humans or by natural phenomena, not necessarily by humans, like I said, by plants or, of course, by other animals as well. And these natural processes can be understood from just a limited number of building blocks. Okay, but now what I want to point out to you is that unfortunately, Dalton had a few errors that really we can't blame on him. His understanding of matter in the fashion that we've just discussed was solely due to his experiences and he observed what was around him. He made a hypothesis as to the behavior of his universe, and he could limitedly test it by doing some simple chemical reactions, and he made a theory. So Dalton's theory was a test of his hypothesis and a conclusion that this was the way that nature worked. Well, now, again, this was done at the beginning of the 1800s. Now here by the year 2000, with a lot more experience under our belts, we have made observances of the behavior of the universe that don't fit exactly in his ideas. Now they fit mostly. We're now just talking about some fringe occurrences that lie outside his predictions and his rules that he established based on his testing of his model. So let's say a little bit about the ideas that Dalton had. And he had ideas with his, or he had problems, it turns out, with his first three rules that he made in the atomic theory. The first one was that all matter is composed of small indivisible particles called atoms. Well, unfortunately, even your mom and them might say that that's not true. You can divide an atom. And this was not figured out for 100 years after Dalton's original supposition. In the early 1900s, it was realized that we could take atoms apart. And there are, as we call them, subatomic particles. And we'll have more to say about them, but I think your mom and them are aware of the subatomic particles. Right off the bat, I think we can all name three. Those are the proton, the neutron, and the electron. So atoms can be broken apart as long as you whack on them hard enough. You get a big enough stick and you beat the atom with enough energy, we can now take atoms apart. As a matter of fact, it really doesn't take a huge amount of energy to take an atom apart. Everybody in this room has taken an atom apart, whether you know that you did or you didn't. And I can tell you what little or what incident or what anecdote is a definite proof that you took atoms apart. Anytime you were walking around in your socks across the carpet and you walked over to the doorknob and you went to grab the doorknob and you shocked yourself, that's a sign that you were taking atoms apart. Literally what you're doing as you drag your feet across the carpet, your feet are gathering electrons from the carpet fibers. And by the time you get to the door, I'm not kidding you, you have gained trillions upon trillions, not just one or two, not just 100 or 1,000. You have gained trillions, again, I'll repeat, upon trillions of electrons onto your body. You are now becoming a huge unit of negative charge. As a matter of fact, maybe we should back up to the beginning of the story. And the beginning of the story is that matter is electrically neutral by nature. There's no net charge in this desktop. There's technically no net charge in me. There's no net charge in the air. Everything is made of charged matter, but there's equal amounts of the positive and the negative. So everything sums up to zero charge. But now when I begin to scrape my feet across the carpet, I begin to scrape huge numbers of electrons with me. And they begin to pile up on me. As a matter of fact, what happens very quickly is they don't like to be piled up on my feet. They quickly begin to spread. And they like to push as far apart from each other as they can. So they will spread evenly over my body so that I have a coating, if you like, of negative charge all over me, all over me. And the more I drag my feet across the carpet, the more of these that build up. Well, of course, what eventually happens is that this imbalance becomes untenable. There's only so much of this imbalance that can be stood before there's so much energy difference in the buildup that it has to be rectified. Nature likes everything to be neutral. So what happens when I get by that door is there's a flow of charge. It's a flow of negative charge, which says, I got to redistribute, I got to get away. There's too much negative charge built up on this guy. And and by the way, guess what's happening to the carpet? As you pull electrons off of it, the carpet is becoming more and more positively charged as you drag the electrons away from it. So you build up this huge imbalance of charge. And as the imbalance of charge gets great enough, then there will be a flow of charge to redistribute. And there's this flow of charge is the little spark that you generate as you get near the door, completing a circuit where now the electrons can quickly redistribute back to where they came from. So every time you get a little spark from touching things with static electricity, you have shown the ease with which you can take atoms apart. Okay, so atoms are not indivisible. There are subatomic particles. And maybe since I'm rambling, let me continue to ramble about something else really even cooler. Think to a nerd like me, even cooler. Not only are there subatomic particles, we now understand there are subatomic particles, meaning the subatomic particles are made up of particles themselves. And probably you've heard some of the names of some of these things, like leptons, quarks, muons, pions. As a matter of fact, and I'm not even kidding you, like we have this periodic table of the elements we use to build molecules and compounds, there's a periodic table of subatomic particles that can be put together to make everything else that is eventually put together to make atoms. So there's a seemingly never-ending hierarchy of building blocks to nature. And the key feature is energy that it takes to break them apart. How much energy it takes to rip apart the various layers over which matter composes itself and collects together. Okay, we're not here to study the subatomic particles. I might say something about them again a little later, but generally speaking, we're going to stop at the subatomic particles as we discuss some of the things about matter. Okay, now what is one of Dalton's other mistakes that he made? Well, in statement 2, he says all atoms of an element are identical. And what he means, they're identical, they're built in exactly the same way. Well, it turns out that they're not. Atoms can exist as what we call isotopes. And isotopes have slightly different structures, and I'll mention this again on an upcoming slide. Now, the importance of isotopes, at least in everyday practical experience, where you might see some importance of something like this, is in the so-called MRI device, the magnetic resonance imaging device. Only certain isotopes of elements are stimulated by the presence of the magnetic field to give the kind of signal that allows us to form an image of our bodies. If every atom in the human body had the same stimulation from the magnets, it would not be able to create this clear picture that is able to be a result of only limited numbers, very small fractions of the atoms in your makeup that are stimulated in this fashion because they're particular isotopes of that atom. Okay, so it turns out he was a little wrong on idea 2. He was also a little wrong on idea 3. And let's remind ourselves what his idea 3 was. It is that when you have atoms combining in definite proportion, you must form the same thing. So if I'm performing a one-to-one combination of carbon to oxygen, I'm always making carbon monoxide. If I can do a 1-to-2 combination of carbon to oxygen, I'm always making carbon dioxide. Turns out he was a little bit wrong there because he didn't have evidence of, like, say, if you combine 5 carbon atoms and 12 hydrogen atoms. I have 3 pictures at the bottom of my screen. One of them might be obscured by the little, you're recording, should I stop the recording? And I apologize for that. But what I'm showing are 3 different ways in which 5 carbons and 12 hydrogens can combine in nature. The first one at the top is what I call a straight chain combination. The 5 carbons hook together, and they each hook to the appropriate number of hydrogens themselves. That's a straight line of them. The other 2 are what I call branched hydrocarbons. Instead of being in a straight chain, there is deviations from the straight chain or branches from the chain. But each of the pictures that I'm showing has 5 carbons and 12 hydrogens. Now, the behavior of each of these is subtly different, not hugely different, but each of these 5 carbon 12 hydrogen molecules will have slightly different properties if you look really closely. The problem for Dalton was in the early 1800s, they couldn't look close enough. They just didn't have the technology to see the subtle differences in the behavior of the properties of these different forms of connection. Now, what I call these, as it says in the red on the third thing, is they are isomers. Isomers are now what we call molecules that disobey the multiple and definite proportions. These are combining in definite proportions, but you're not forming exactly the same material from the 5 carbons and the 12 hydrogens. Now, I will give him credit. His idea number 4 seems to hold water. If you have a chemical reaction, the atoms on the starting material are rearranged into atoms of the finishing material. None of the atoms is lost. Every atom that began in the reactants has to show up in the products. You can't sweep any atoms under the rug. You can't pull any atoms out of thin air. There is, as we say, conservation of matter when materials react. There is also conservation of energy. All the energy that it took to build the original materials that you're taking apart shows up in the energy that evolves when you build the new materials as finishing products. If there's extra energy compared to the start to the finish, you release that energy, maybe in the form of heat, maybe in the form of light, maybe pushing the air, maybe making sound, maybe all 4. If it takes more energy to build the product than it took to build the starting materials, you better input energy. Where do we see evidence of that? Like I said, with the sun. The leaves, the tree will not grow just by taking carbon dioxide and water out of the ground. It has to combine that with the energy from the sun in photosynthesis to build the material that allows it to become the big tree. Okay, so now what we're going to say is that we have basically completed our introduction to the idea of the atom, but now let's delve into this subatomic thing because it's very, very important. Let's look just briefly at our unraveling of the atom itself and how we came to the point where we can understand the structure of the atom itself. And believe me, we cannot do it justice in the next 30 minutes, which is the amount of time I'm going to spend discussing this with you. This isn't a concept or this has been an idea that took not a decade to evolve, it took a century for us to understand the subatomic nature of matter. But the ramifications of our understanding of how atoms have been put together have led to incredible advances, maybe some in a good way, but many in a bad way as well. All the transistor circuits that we have and all the semiconductors that we have in our nice little smartphones that we all carry around for each other or carry around and use to our great advantage at this time. All of these came about from our understanding of the subatomic structure of matter. Even more, maybe not so great things like the development of crazy weapons like the nuclear bombs and things like this came about from our understanding of the subatomic structure of matter. And maybe we could say things like generating power in the form of a nuclear reactor. That certainly came about from our understanding of the subatomic structure of matter. Okay, so let's look then again, as I will say briefly, just over probably the remainder of the period here, at some of the where the model and how our understanding of this subatomic structure came about. Remember, this again comes from the so-called scientific method. At the time of Dalton, it was completely wrong. They just didn't have enough evidence. They made the hypothesis that actually this had been made by Democritus a long time before. It was returned to by Dalton, and Dalton returned to the concept that atoms were indivisible. And essentially, there was nothing below the atom. So you could think of like an atom like a bowling ball. But the bowling ball that made the oxygen atom was different than the bowling ball that made the carbon atom, which was different than the bowling ball that made the gold atom. But you could not take the gold atom apart. You couldn't take the carbon atom apart. You couldn't take the oxygen atom apart. So there was no, as we would say, subatomic structure to those atoms at the time of Dalton. Well, finally, around the year 1900, this guy came along. And believe me, many others were working on similar things, but he was the first one to be able to pull this off. What he did was he placed atoms in a very highly charged electric field. And it began to, there was so much energy in the field that he was putting them in that it began to do strange things to them. And it began to make a beam of flowing atoms that came off of a plate. He had a thin plate of atoms. And when he put them in this, a large electric field, which means a large separation of positive and negative charge, it began to rip apart the previously neutral material. Okay, so what I'm getting at is he took a piece of natural metal and he noticed that it wasn't charged in any way. It didn't have a net positive. It didn't have a net negative. So it was electrically neutral material that he had. And you could look at it and feel it and touch it and put meters on it, and it showed no positive charge. It showed no negative charge. It is, as we say, electrically neutral. Then when he put it in this strong field with a high energy subjecting to this piece of metal, suddenly it began to fly apart in the sense that the metal became positively charged and a stream of negative charge flew out of the metal. So he was able to show that there was a negatively charged amount of matter present even in neutral matter. All neutral matter had negative charge within it. Well, what he also noted was as the negative charge was being able to be drawn away from the originally neutral piece of metal, that the originally neutral piece of metal was becoming positively charged. And the amount of negative charge he withdrew was exactly balanced by the amount of positive charge that was gained in the remaining piece of metal. So the conclusion was that all matter was, even though it seemed ultimately to be electrically neutral, it was made up equally of a certain amount of positive and a certain amount of negative charge. And only when subjecting it to a huge amount of energy could you separate the electrically negative from the electrically positive. I offered to you that we now understand that it really doesn't even take all that much energy. Once again, if you walk across the carpet in your socks, you are separating charge, and you're separating a fairly large amount of charge, believe it or not. Again, I will repeat, believe it or not, trillions and trillions of electrons are coming with you when you do that. Okay, so once he came up with the conclusion that this was occurring, the important thing was now to modify the scientific method. The scientific method, according to Dalton, was the hypothesis is that there is no further divisible matter below the atom. So the hypothesis is the atom is indivisible. Now, Thomson has done an experiment that says, wait a minute, I seem to be dividing seemingly neutral atoms into individual charged particles. We need to modify and come up with a new hypothesis of the atom itself, because I am now showing that there's something wrong with Dalton's model of the atom. Now, here's what Thomson had to go on. There was certainly positive and negative in all this neutral matter. Another thing he was able to discern was that the negative was way tinier than the positive. How was he able to do this? By varying his electric field that he sent the charge through, it would curve the charge. And he could tell from the amount of variance of the field that he had to employ, the magnitude of the curvature that would be generated. He could come up with an idea of the mass of the charge that was being curved. And it was easily recognizable that the negative charge had the same value of charge as the positive charge, but the mass of the negative charge was way less than the mass of the positive charge. So as they're developing a new model, his model has to account for the fact that there's equal amounts of negative and positive charge, but the positive charge is way more massive than the negative charge. So the model that Thomson came up with, he called his Plum pudding model. He was a nice British guy, so he probably said, it's plum pudding. And what the plum pudding model said was that there was a massive pudding of positive charge. Embedded in it were small plums of negative charge. So the vast majority of the atom, where all the mass seemed to reside, was positive. Then sprinkled in there would be little dots of the negative. And when he subjected this to a highly charged environment, he was able to now pull loose the plums from the pudding. Okay, so this was what we would call the original plum pudding model attributed to J.J. Thomson. Every chemistry textbook has this story in it, but they don't tell. What they basically say is, this guy was an idiot. They don't say that. But their implication is, he got it wrong. Thomson got it wrong. They neglect to point out how careful Thomson was in his experimentation. They neglect to point out that he was the one that found the electrons in the first place. Yes, his model of the atom turns out to be wrong, but does he deserve to be stated in all chemistry textbooks and remembered in all chemistry textbooks as the person who got it wrong? No, it's kind of unfair. All chemistry textbooks have this guy's name, and basically all chemistry textbooks say, this guy got it wrong. And I again will say I think that's a little unfair, because if it wasn't for his careful experimentation, we would never have known, or at least not at the period of time that we found out, we would have never found out as quickly that there was subatomic structure to atoms. Okay, so he makes this model, and it turns out to be not so good. And where it was revealed that it was not so good was by a hated rival, believe it or not. This guy had a rival who was a contemporary of his, who they literally detested each other. These two guys couldn't stand each other. And as soon as he published this model, his number one arch enemy scientific rival said, okay, I'm going to make a test. And I'm going to test his hypothesis with my test. And I'm going to see if his model holds water. And that guy was the name Ernest Rutherford. So again, Rutherford and Thomson were not the best of friends. Believe me, scientists are shallow and petty, and they don't have much going on in their lives. And to them, this is like it. This is like, this is like it's going to be with Tampa Bay versus the Saints. This is what it's going to be like. It's going to be pure hatred of each other. It's going to be similar, at least to people like me. That's what I would like make it equivalent to. Forget Atlanta. It's going to be the Saints and Tampa. That's the story. Okay, but in any event, this Rutherford says, okay, so he thinks there's a massive amount of positive charge embedded with a little bit of negative. So here's how I'm going to test that. He made himself another little foil, and he put it again in a powerful field, but this time, instead of pulling loose the negative, he was able to make a beam of the positive. And the positive was big and massive. Remember what I said before was that the negative was tiny. And when he made it, when Rutherford Thomson originally made his beam, it was not very much mass to that beam. Well, Rutherford's beam was made from the positive. And granted, to me and you, it's not much weight, but the mass of the positive beam was incredible compared to the mass of the negative beam. And he shot his positive beam at another sheet of metal. So he shoots the positive beam at the sheet of metal, and what the positive beam did was very critical. When the positive beam impinged upon the sheet of gold metal, some of them went right through, as the picture shows. Some of them bounced straight back, and some of them were just bent when they went through. So we would say a portion of the beam was deflected, a portion of the beam went right through, and every once in a while, one particle of the beam would bounce straight back. So what Rutherford said was that there's got to be, so he made these, I say all these in words here. He makes the positive particles, he shoots them at the gold, and they either deflected at very sharp angles, they pass straight through, or bounce straight back. So he had to modify a model that could explain how could some of these go through, how could some of these bounce back, and how could some of these just be slightly bent. Well, what he said was that's because an atom is constructed just like the solar system. Rutherford named it the planetary model. So he was shooting these positive particles that were kind of like asteroids. And when he shot the asteroid through the solar system, most of them just passed right through because there was a big empty amount of space between everything in the solar system. So there was plenty of room for these asteroids to fly right through without hitting anything. Occasionally, they glanced off one and bounced at an angle. Occasionally, they slammed right into one and seemed to bounce straight back. So his model was built so that the massive part of the solar system was in the center. So what he said was that all the positive charge was collected in the center of the atom. And he called that the nucleus. So the nucleus holds all the positive charge. And that's the massive part of the solar system. Just like the sun is way, 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 way more massive than the Earth, and essentially the gravitational pull of the sun pulls the Earth as well as all the other planets around the sun. So the nucleus has all the positive charge in the middle, but many of his contemporaries said, wait a minute, I know that a hydrogen atom has half as much positive charge as helium. They could figure that out. I know that a lithium atom has 3 times as much positive charge as a hydrogen. I know that a beryllium has 4 times as much. I know boron has 5 times as much. I know carbon has 6 times as much. So you're going to tell me that all that positive charge is piled up in one central location. Well, that don't make sense. Why doesn't that make sense? Because it was well known that positive charge repelled itself. When you try to pile a whole bunch of positive charges together, they push each other apart. Only opposite charges can pull together. So Rutherford's model was immediately debunked because as you built up positive charge, it could not all be localized in the same place. So what Rutherford said was, okay, well, there's something else going on here. There's something we don't know that's holding the nucleus together. I'm going to propose there's another particle that we haven't figured out. Now, I'm going to tell you what, this right here is a stroke of genius. His model was not working. So people had tested his theory and provided a reason as to why his theory wouldn't work. So he made a new hypothesis. His new hypothesis was, there's something we don't know about. And here's how I know that for sure. The ratio of positive charge in a hydrogen atom compared to a helium atom doesn't match the mass. There's a certain mass to charge ratio. When I take apart a hydrogen atom, I can tell by when they fall apart, there's 1 unit of positive charge in the hydrogen atom, and it has a certain mass. When I take a helium apart, there's 2 units of positive charge, for sure. But there's not 2 units of mass. There's actually 4 units of mass. So there's more mass to hold the 2 charges together than there needed to be in an individual charge. When I take lithiums apart, there's 3 units of positive charge, but there's again, about double the amount of mass. So there's 6 units of mass. So there's some missing mass relationship in the nucleus that we haven't unraveled. And I'm going to claim it doesn't have any charge. It has mass, but no charge. So I'm going to call it a neutron. He even named it. Rutherford named this unknown particle, which was kind of like the nuclear Velcro, which enabled the positive charge to all localize in a nucleus without pushing itself apart, because like charges don't want to be together, they want to be apart. So there's a third magic subatomic particle that enables the nucleus to be held together. Well, as soon as he made his prediction, immediately, like scientists want to do, they dove on it and said, let's go looking for this. And very shortly after Rutherford's prediction, an individual by the name of Chadwick was able to find a neutron, find a particle in the nucleus with no charge, about the same mass as the proton, and it held the nucleus together. Anytime you have more than 1 unit of positive charge in a nucleus, you need this magic particle in there with it. You cannot build a nucleus of 2 positive charges alone. They won't stick together. But you have to put equal numbers of neutrons, it seems. Not in all cases, but at least typically the same number of neutrons go in there as do the positive charges. This glues everything together. Now, the model as to how that works is way beyond what we're going to be getting into here. How the neutron works to hold the nucleus together. That's really, if you truly want to know the answer, not a fully understood process. It's not a simply explained process, but somehow neutrons act, as I said, as nuclear Velcro. So the neutron is going to glue together all the positive charge and keep it localized in the most massive part of an atom, that being the nucleus. So this is Rutherford's model of the atom, and we will call that the planetary model of the atom. Okay, wow! Guess what? Okay, we'll say, I guess that isn't on this slide. Okay, so I say here at the top that Rutherford proposed the idea of the neutron just to hold everything together. Now what we know are that these are the three familiar subatomic particles. Again, I'm pretty sure your mom and them are familiar with them. The proton, the neutron, and the electron. All atoms are composed of protons, neutrons, and electrons. For all intents and purposes, every proton is the same, every neutron is the same, every electron is the same, and they are all used to build all the elements. So what makes a carbon atom different than, say, an oxygen atom is simply how many protons, neutrons, and electrons you collect together. That's it. What makes a gold atom different than a platinum atom is how many protons, neutrons, and electrons, the exact same particles. It's how many of them you put together in a platinum compared to how many of them you put together in a gold. So we now have this further deeper understanding of the things that go together to make materials. There are these subatomic particles. As I mentioned, there's actually subatomic particles. We're not going to concern ourselves with those. We're going to stop here at the subatomic particle. I'm showing you on this particular slide that the charge of these things and the mass of these things have been measured. Let's say something about those numbers. They're little. They're very little. The power of 10 that these are expressed by is incredibly large. So there's many decimal places. As a matter of fact, for the proton, its charge is plus 0.18 For its mass, it would be 0.26 So these are incredibly tiny numbers for the mass and charge on these particles. Notice the neutron has 0 charge, no charge at all on the neutron. It is electrically neutral. Another thing to say, I'm listing the charge on the proton and the electron to only 3 digits of accuracy. The number part of the scientific notion is 3 numbers. First, I will point out to you that this number is known to like 9 digits of accuracy. This is an incredibly well-known number. As I talked about with you before, when numbers are known to that degree of accuracy, very careful examination has been done on them. So these numbers have been measured very, very, very carefully. And what we have found is that they match numerically to all digits that we can find. So the charge on the proton is exactly the same number as the charge on the electron. And theoretically, what is predicted was if you could measure this number out to infinity, meaning measure every digit possible of the number that fits the charge of the proton compared to the number that fits the charge of the electron, they would match exactly forever. The charge on the proton is exactly numerically the same as the charge on the electron. They match perfectly. That's incredible when you stop to think about that. Now, can we prove that? The answer would be that we can't really. It is predicted that the universe operates under the premise that these charges are exactly equal, but their difference, of course, is their sign. As we all probably are aware, we say that protons are positively charged. we say that electrons are negatively charged. Now, the concept of that I will have to offer to you is deep. The fact that the charge on the electron is negative and the charge on the proton is positive is really a manifestation of our attempt to model the behavior of their action. Now, here's what I mean about that. Let's turn to another familiar field force. What a field force is a force that emanates through space without contact. This is bizarre. I will say it again. A field force emanates through space without contact. Meaning, if I want to exert force on you, I must lay my hands upon you and push. If I want to throw a baseball, I must hold it, contact my hand, and put the force directly into a baseball. So many forces, particularly the ones we exert, are contact forces. I cannot make force without contacting. A bulldozer cannot move dirt unless it is contacting the dirt. But there are forces in nature that operate through space, like gravity. I can lift something above the surface of the earth and let it go, and the earth pulls it to it without touching it. So this works, forces like that work through the space itself. So they provide action at a distance, we say. It causes action without, that's just so bizarre. Now, I will say this, it would be so cool if I could go to this paper towel rack and go, and make it move. If I had the ability to provide action at a distance. I don't. But massive objects do. The gravity of Earth pulls everything to it. The gravity of the sun pulls the Earth to it. So there's an attractive force generated through space that we call a field. We call it the field of gravity. Now, not only does mass exert force, charge exerts force. And I think we're all familiar with that. Charges can attract each other. But interestingly, charges can also repel each other. Charges not only pull each other towards themselves, they push each other apart. So for gravity, you don't need a sign. Gravity's always attractive. There's no repulsive gravity. So we didn't need to put into the concept a direction. Charges either push or pull, depending on their plus or minus. So that's why there was a necessity of a sign. Pushing or pulling, a plus or a negative. Now the push or pull can be the same, but there's a direction to the action. So that's why scientists had to give charges signs, so we could indicate which way the action was going to occur. Pretty cool and pretty crazy, right? Things like that excite me. I mean, whatever. If they don't, stuff like that's cool to me. All right, I can see I'm at the quit time. Okay, please remember to go online and do your little assignment for me. Please humor me. And again, after we talk on Wednesday, I'll put our last of the first test ones out there. So until next time, peace out.